Imagine this, you are at a car race with your friend. You are chilling in the crowd and your friend has gone off to grab some snacks. Just as your favorite car is about to zoom past, you shout for your friend to hurry up. Now, as the car speeds by in front of you, your friend was running in the same direction. Do you think the speed of car will look the same to both of you? If the car's speed was 100 meters per second and your friend was running at around 10, then for him it would look like the car is moving at 90, that is 100 minus 10. This difference appears because of your relative motions. For you, you are at rest, and for your friend, he is at rest. But relative to each other, you are both in motion. That is why the same car's speed appears different to both of you. Now imagine replacing that car with a flash of light. Do you think the speed of light would feel different to each of you? Would your friend measure it differently, just like he measured the speed of car differently? Does the speed of light slows down for an observer moving really fast? No, even if he is moving as fast as possible, the speed of light will be exactly the same to each of you. Look at these two situations together. On one hand, the speed of objects changes depending on the observer's motion. It is different for everyone. But on the other hand, the speed of light stays the same for all, no matter what. I know this fact seems just as weird to you as it does to me. In this video, we are going to dig into it and find out why the speed of light is a universal constant. First, we need to realize that nothing around us or even in the entire cosmos is truly still. A tree might seem stationary, but it is rotating along with the earth, and then the earth is moving around the sun, which isn't standing still either. All stars, galaxies, everything is moving in some way. Some things might seem still to you, but at the same time, it would be moving for someone else. Rest and motion are connected, and if no force is involved, these two states are pretty much the same. Let us imagine for a moment that you are standing still on the ground, completely stationary. Conspiracy theorist. Anyways, and you throw a ball straight up. It is simple, right? The ball will fall back into your hand. Now, if you throw this same ball while standing in a moving train or car, what happens? Will it still fall back into your hand? Or will it land behind you? At first, it might seem like the ball will fall behind you, since when you drop something, it usually comes down from where you left it. But no, the ball will fall still back into your hand. For an observer standing on the ground, both you and the ball are moving with the train. So, when you throw it up, it is still moving forward, and it eventually lands right back into your hand. Even though the ball's trajectory might look parabolic to that stationary observer, for you, it is the same straight up and down path it always was. So, how can you tell if you are stationary or in constant linear motion? You cannot. These two situations are exactly the same. There is no universal frame of reference in this universe. Now let us talk about light. Think of it like this. When you disturb the surface of water, a ripple spreads outward from the point of disturbance. But it doesn't reach everywhere instantaneously. It takes time. This disturbance travels at a finite speed. Light behaves similarly. It is a wave, an electromagnetic wave. When a charged particle suddenly changes its state of motion with any type of acceleration, it emits electromagnetic waves. Changing magnetic fields produces changing electric fields, and changing electric fields produces changing magnetic fields, which is how these waves move forward. We can determine the speed of electromagnetic waves by solving Maxwell's equations, and there it is. C equals 1 over square root epsilon 0 times mu 0. Notice that this equation does not refer to any specific reference frame. Light does not need a medium to travel through. The constants epsilon 0 and mu 0 are fundamental constants that describe how space reacts to electric and magnetic fields. Essentially, the speed of light emerges from those fundamental constants. So, shouldn't it also be a fundamental constant? One could argue that since the speed of light is a constant, there must be a reference frame that is stationary for everyone. only then would c be a constant. But we have already established that no such reference frame exists in this universe. If it did, light would appear slower to a fast moving observer. So we now have two facts. First, there is no universal frame of reference. All motion are relative. Second, the speed of light is a fundamental constant. The only logical conclusion is that the speed of light must be a universal constant. Let us differentiate between a fundamental constant and a universal constant. The value of a fundamental constant can vary for different observers. For instance, that car was moving at a constant speed of 100 meters per second, but you and your friend have measured it differently. A universal constant, on the other hand, have the same value for everyone, exactly the same. So the speed of light is a fundamental constant, but nature didn't decide for whom or in which frame it should apply. So it ends up having the same value for all. We often assume that space and time are absolute, the same for everyone. But think about it. Time slows down for a moving observer, and length changes too. This all happens because the speed of light is consistent.